I am Dr. Groves, your session chairman, and I have an easy job in which I am going to introduce one speaker, and he's going to be a very interesting man to introduce. We're honored today by having as a keynote speaker Richard H. Cobb, president of Mathematica Products Group of Princeton, New Jersey. Dick Cobb is the world's leading expert in RAMIS-2, a fourth-generation language which shifts the emphasis of large databases from the DP department to the end user. And in reading over the notes, I would suggest that this meeting is going to be of extreme importance to two groups of people. The first group is the businessman who goes to his DP department and says, I would like a report on last year's profits by department and project. And he is told, well, that will be 2 weeks away because of the overload in the application staff. And that 2 weeks is a moving window that dates from today. The other group would be the people in the application staff who are COBOL programmers. And for some years, I've been saying that a COBOL programmer should ask himself, if COBOL was declared a non-language tomorrow, would I be an asset to my company the day after? And it hasn't happened yet, but I would suggest that we consider that question. Dick Cobb has worked in the areas of operations research and systems analysis, as well as database management, and has published numerous papers on these subjects. He has a master's degree from the Rensselaer Polytech Institute, which is a tertiary institution that doesn't have a parallel in Australia. And before joining Mathematica, he was an adjunct professor of mathematics and has also worked for Coopers and Lybrand. So we're fortunate in having a gentleman who not only knows his subject, but he's been in the academic world, the business world, and the computing world, and so he can tell us how to bridge these. I might mention that Mathematica has their own office here in Australia, and so if you want to get in touch with Mr. Cobb afterwards, why, I'm sure we can let you know where it is. And it's a pleasure to introduce Dick Cobb on the evolution of dialogues between people and computers.
Well, thank you very much. I am delighted to be here. I have enjoyed my days here so far in Australia, and I'm sure I'll enjoy the rest of them. I hope that a few of the things that we say today can be of use to you. And what I really want to talk about is spend a few minutes discussing how the dialogue between people and computers, or between computers and people, have evolved over the years. They're interchangeable. I want to look at where we have been, where we are today, and where I think we'll be in a few years. I also want to ask why we are not taking full advantage of what it is possible to do today. We can now see clearly 5 stages in the evolution of languages. First, we had machine language. Then we moved to assembler. Then we moved to high-level languages like Fortran, COBOL, PL1, BASIC, C, non-procedural languages, and not the last case is knowledge-based languages, the areas that we're just moving into at this very time. What I'd like to do is say a few words about each of these, concentrating on the later generations. I think they're the ones of more interest to us. I would also like to say a few words about the evolving user interface with computers. In addition, I will touch on the impact of the latest generation of languages as having on the growing movement toward consumer computing. I see computer languages are very important for several reasons. First, we are going to see continued and increasing massive investments in information processing. The projections are that in the next 5 years, U.S. industry will spend $1 trillion with vendors of information processing equipment, which represents just 7.5% of the U.S. GNP during the same period. I suspect that I don't have the exact data for Australia, but I suspect that the ratios are very similar. But if we expand our definition of information processing to include the costs that are incurred to support information workers, those people who use the information equipment that the vendors are selling, and we assume no great productivity increases, and we also assume no great increases in labor costs, then we'll see that the expenditure in the same period of time in the United States is forecast to be $10 trillion, which is just roughly 2/3 of the gross national product. That's clearly something that one has to worry about. The differences between these readily identified costs and the less readily identified costs is first was studied by somebody named Paul Strassman, and he referred to that as the information iceberg, all the cost below the waterline. Even small improvements in these very large numbers will be very beneficial for corporations, and even more importantly for society as a whole. I believe it's the improvements in language that will provide the leverage to make these improvements. Computers have been used in two principal areas to support business: supporting operational systems such as accounting or manufacturing control systems, the list goes on, or aiding individuals in order to increase their own personal productivity. This chart is originally developed by two professors at MIT, Gorey and Scott Morton, define the world of business data processing. Going across the columns, I believe you can see that problems go from being operational problems on your right to on your left to strategic problems on your right, basically the duration of the consequences of the problem. Going down the rows, completely structured problems at the top to unstructured problems at the bottom. Typically, the domain of business data processing has been the upper left-hand corner, solving these highly structured operational problems like accounting and payroll systems. The area of the province of decision support operations research has been the lower right-hand corner, the decision support area, solving these unstructured problems. Basically, I think if you look at that chart, it defines the whole area. The first point of operational problems in the upper left-hand corner, decision support, increased personal productivity in the lower right-hand corner. As you can see, when computers are used in the first area, the effort of developing most of these applications is the responsibility of one of the more than 625,000 computer specialists in the United States, or here in Australia, the 40,000. This activity is relatively far advanced. The impact of computers used in this area has been great. Today, most companies would cease to run if their computers ceased to function. The main area of improvement that can be made in this area is to increase the productivity of the computer specialists. This can be done by improving their ability to converse with the computer. The use of the computers in the second area, typically called consumer computing, is less advanced. But the use in this area is growing very fast. Companies are setting up information centers. We see executives buying personal computers by the hundreds. We are rushing headlong into giving every one of our 50 million office workers direct and personal contact with computers. It is this area where we need to look for much greater improvement in carrying on dialogues with the computer. We need to teach the computer to talk to people, not to continue to try to teach people to talk to the computer. All too often when we think about computers, we think of hardware and the very, very large decreases we have experienced in the cost performance. But it is not hardware alone that makes computers useful. The other main component is systems software. It is the system software that establishes the rules by which computers and people can carry on a dialogue. I think by focusing on the effectiveness of their investments in the information processing, to focus on these investments we'd like to know where we've been so we can look and see where we're going. When I'm talking to managers, the reaction I get is something like, don't talk to me about dialogues between computers and people. I know all about that. They say computers and programmers are hard, if not impossible, to deal with. The people who use them don't understand what we want. You can never get what we want. They always are late. The list of complaints goes on and on. I think the following story represents their views toward communications with computers. This story happens to be with a Texas sheriff. Texas in the southern part of the United States, right above Mexico. It turns out that he arrested a person who he thought was a bank robber, who turned out only to speak Spanish. So he wanted to question him, needed a translator, hired a translator, started to ask the translator, he wanted to interrogate this purported bank robber, and he said to the translator, ask him why he robbed the bank. The translator translated to the bank robber, purported bank robber. Purported bank robber responded back in Spanish, I didn't rob the bank. The translator told the sheriff. This dialogue went back and forth for some time. It depends on how long you'd like to drag out the story. But And finally, the sheriff pulled out his six-shooter, put it up against the head of the bank robber, and said to the translator, tell the bank robber that if he doesn't tell me where the money is, I'm going to blow his brains out. The translator turns to the bank robber and repeated that to the bank robber. The bank robber said, the money is in the saddlebags on my horse out in back of the saloon. The translator turns back to the sheriff and says, he said he doesn't rob the bank and doesn't know where the money is. I suspect that very often when you, individually in your corporations, wherever you are, talking with suppliers, talking with customers, you very often conclude that we have a communications problem. You say, if we can improve our communications, that problem will be resolved. I believe the same is true with both your companies and your personal use of computers. The stages of evolution of our dialogue with computers now span slightly more than 30 years. The progress has been very rapid in that short period of time. At the very beginning, communications between people and computers was based on the language of the computer itself. This generation was characterized by the scientist or engineer in the white coat. It was thought at that time we would have a few highly trained people who could keep a few very expensive computers working on the hardest and most difficult problems. I remember when I was in the early 50s, when I first started to work for General Electric Company in Evendale, Ohio. We had a famous person who was in charge of our computer center. He would like a round room, so they built him a round room so he could do what he wanted. He liked a round desk, so they had a round desk. It had a hole in the middle, so he could sit in the hole like in the hole of the donut, and he could spin around and he could talk to the various people who worked on projects sitting outside the ring. He liked tropical fish, so they had built-in fish tanks all around the room so that they could watch a tropical fish floating around as he thought and worked on these problems. It got so bad that the General Electric Company had to buy out the biggest fish store in downtown Cincinnati so that the vendor of that store could maintain the tropical fish. That was the world of computing in machine language days. It was very labor intensive. In terms of communications with computers, the computers understood well-structured patterns of zeros and ones very well. This generation of languages is still with us in the area of designing computers. That's how a computer architect now designs computers. Then in the late 50s, the second generation of software began to emerge. This generation was based on the assembler language. It improved communications a fantastic amount. Those of you who didn't live through that just have no idea the increases in productivity that caused. It transferred a lot of work to the computer, but it was still very labor intensive. This generation of language is still with us, largely in the people who develop systems software. The third generation followed the second very quickly when we moved to what is now called high-level languages, such as COBOL or Fortran. These are procedural languages. This generation of languages is still widespread use. This generation has been extended with many supplemental system tools, such as report writers, database management systems, and with application products where you directly obtain an application such as a general ledger or an MRP system. These application products have been written in third-generation languages by a vendor instead of being written by your staff. This extends productivity. The net result is that third-generation languages, supplemented by these programming aids, and the application products have led to very important productivity. And the generation of languages has spurred the great increase. It's what's caused the information revolution we have in the last 20 years. The accomplishments during this time have been huge. Look at the state, the number of computers, tens of thousands of computers, limited supply of people to keep them going, to care and feed them, expenditure levels, even with hardware costs decreasing at about 40% per year, increasing at 15% per year, total expenditures. I'd like to say a few words about database management systems. These are not technically languages, but they're very important in the evolution of languages. And in fact, the next generation of languages is non-procedural that we'll talk about could not exist if it was not for DBMSs. The world before DBMS was characterized by each application being responsible for knowing and understanding the data structures they wanted to access. When a change occurred in a data structure, all applications were affected. To solve this problem, the concept of DBMS is involved. to provide a data-independent access method. So in theory, if we had a change in the data structure, the application would be immune to change, thereby making it easy to develop new applications and reduce environmental maintenance. Early DBMSs, and even most DBMSs today, are what are called navigational systems. And these systems have given up much of their original goal of data independence. IMS and IDMS are good examples of such navigational systems. Navigational systems require a high degree of knowledge on the part of the programmer in order to use them, and a large amount of the intended data independence was given away. They had to do this in order to be able to model all business problems, business data processing problems. The result was that such concepts as multipath, we'll soon see that databases that don't provide data independence are not suitable for non-procedural languages. In summary, the weaknesses with navigational systems are relationships are predefined, and programmers must be aware of all the pointers. To eliminate these weaknesses, the concept of structure-independent databases were developed. Very often databases like these are called relational. Very important concept. With a structure-independent database, relationships are defined dynamically, and the user is not concerned with the structure. Structure-independent databases are a prerequisite for the next generation of languages or non-procedural. Another very important aspect of databases is that they ought to provide access to external data. First, as represented by this slide, in the United States business people will spend roughly $1 billion this year to access external data. I'm not sure what the level here is. I suspect it's lower as a percentage, but growing very fast. It is desirable to have the same mechanism for accessing both internal and external data. A second reason that you want to be able to do this is that on your central computer you probably have a lot of different data structures. If you access all of these different types of data at the installation, it is able to protect previous investments, as well as being able to spend money on new applications and not redoing old applications. Another very important capability of database management systems is that you ought to be able to relate data from multiple sources, even multiple sources not contained in one database. It is not only necessary that you can do this, as I said, for data in one place, but in multiple places. Now, maybe to spend a few words talking about non-procedural languages. I think a very important improvement. The initial idea of fourth-generation languages began in 1967 at Mathematica and began to have a real impact in the late 1970s. And now the rate at which companies are replacing the third-generation technology is increasing. The idea behind these fourth-generation languages is non-procedural. Fourth-generation languages are a new breed. They have extensively expanded the community of users, having direct contact with today's computer. They've introduced the concept of the jargon word user-friendly. Acceptance of fourth-generation languages has not been easy. During a speech I made in 1977, I stated my belief that fourth-generation languages would replace third-generation languages such as COBOLs in the 1980s. We still have 7 years to go, as of today. The conference moderator balked in total disbelief and asked for a show of hands from those people in the audience who agreed with this statement. Of the 150 plus people in the audience, not one person agreed. 5 years later, however, the tide is turning. Opposition to these earlier predictions is less intense and in some cases non-existent, as more and more people have experience with these languages. What constitutes a fourth-generation language? What we mean by non-procedural is a language that's results-oriented as opposed to the method-oriented procedural languages of the first three generations. With a fourth-generation language, the person using the computer tells it what is wanted as opposed to telling it how to do it. The non-procedural fourth-generation languages allow the user to communicate with the computer in a language that much more resembles English than the traditional computer languages. When comparing the programming approaches of the earlier fourth-generation languages, it is important to look at each step or action that had to be taken. With the third-generation language, or first or second, the programmer starts with a statement of the problem, and then moves on to generating programming specifications in the second step. The third step finds the programming code, defines the programming code. In the fourth step, the programmer debugs the program by identifying any programming errors or inconsistencies in the program specifications. The fifth step should yield the final solution unless the programmer finds that was originally intended to be the solution is not actually needed to answer the question, either because didn't understand, or probably more likely because the process has taken such duration that the world has changed since the original specification until you're ready to implement the solution. This tedious and time-consuming process discourages many people from requesting the solution to a problem. In contrast, the steps with programming using a non-procedural language begin with a statement from the programmer or end user of what is wanted. For instance, if you want a sales report containing the number of items sold by product, customer, month, and year is desired, fewer than 10 lines are required to produce such a report, compared to the hundreds of lines that you might require otherwise. To understand the revolutionary approach of fourth generation, let's take a look at how languages have evolved. That slide has a typographical error on it, for which I apologize. That should say procedural languages at the top. The computer languages in the first three generations are closely tied to computer hardware and are derivatives of the work of the late mathematician John von Neumann at the Institute of Advanced Study located in Princeton. With the von Neumann-based languages, the programmer has two responsibilities: to define what is to be done and to define the control of the flow of the program. Based on these responsibilities and the fact that these languages are driven by characteristics of the machine they run on, von Neumann languages are labeled as procedural languages. The first generation of procedural languages were binary-oriented, as we have said, followed by assembler, and then a decade later, the high-level languages. In the earlier two generations, the role of the program counter was very explicit. That was apparent in the control. Third generation languages, for the most part, disguised this role, leading to a lack of discipline in the management of the program counter. In order to impose discipline in the management of the disguised program counter, the concept of structured programming was introduced by Harlan Mills, now of IBM, and previously of Mathematica. The fourth generation non-procedural languages altered this approach to programming and the role of the program counter. The concept behind a non-procedural language is to transfer the entire concern about program flow or the value of the program counter from the computer specialist to the computer itself. This new approach opened the doors for continuous evolutionary development of new generation of computer languages. For instance, fourth generation languages were forced to include a database management capability, data maintenance capability to support non-procedural programming. Because of their what is wanted and not how to do it approach, fourth generation database management capabilities must be judged to what degree they provide structure-independent access to data. If a fourth generation language is without structure independence, a user must know how the data is organized in order to ensure that navigation through the data place will retrieve what is wanted. With structure independence, you don't have to do that. I believe that only one fourth generation language has rigorously adhered to this standard of structure independence. Let's look at a small example. Assume that we would like to prepare a report showing the total units sold for each product by customer, by month, and year, with a subtotal for each customer, and each new customer starting on a new page. In a fourth generation language, this would be a typical procedure to do that. This example here is a flow chart taken out of a book on programming logic that was this particular problem. It has a book that specifies a lot of these kind of flow charts. And it goes on and on. I think that might be the last one. I think what's significant there is to define the actual real solution to that problem only requires significantly less than 10% of the boxes on that flow chart. The rest of the boxes define how to control the programming flow, how to worry really about the program counter. And that's where all the productivity increases will come from, do come from non-procedural languages. I guess I forgot one. Now, if I wanted to do this in COBOL, a typical COBOL program, if you're really good, might require only 500 lines. If you're not quite so good, require about 1,000 lines in order to do that simple request. Again, all the stuff is in the housekeeping. So to summarize, the benefits of fourth-generation languages are, first, they're results-oriented, very important. They give productivity increases of at least 5 to 1, and very often 300 to 1. They are for both computer specialists and end users. And finally, you incur no efficiency penalty. In the early days, these approaches clearly were more expensive than COBOL procedural language programs. Today, with the evolutionary improvement, today, if anything, they're more efficient, so you don't incur efficiency penalty. I think one thing that's really worthwhile is to look at the bottom line, look at really what are the economics of fourth generation versus third generation. Let's assume that we have a programming person, one programming person, whose total cost is $25 an hour. These are US dollars in this example. I can justify $25 there. That includes computer time that the person may use. The project duration will be 8 months, not too atypical. The payback period for the project, once it's completed, will be 1 year. And the application life will be 2.5 years. Very typical kind of specifications. So if we start off, we start developing the first project. We complete it in the third quarter. We begin to derive some benefit initially. We get more benefit in the fourth quarter. Instantaneously, our person starts on the second project in the third quarter and hasn't finished it by the end of the first year. So the cumulative benefit to the corporation at the end of the first year from this endeavor is $40,444 negative. If we extend the graph for 3 years, if we look at the yellow bars, that's the total quarterly benefits. The cumulative benefits are on the orange line at the top. The cumulative development costs are at the bottom. We haven't assumed any pay increases for this programmer. The cumulative costs are showing going down, and the net benefit is going up. We see that the person has become, the corporation is net positive sometime in the third year. If we would do the same case study for fourth generation languages, assuming only a conservative 5 to 1 productivity increase, I've skipped over the slide, the flow chart, the spreadsheet that would show the analysis of this. We see the net improvement. The cumulative benefit is now almost $1 million in 3 years. You can see that the break-even, the turnover point is now sometime in the third quarter of the first year. Looking at it selfishly from a programmer, if I was a programmer, I would rather be this programmer when it came to bonus time at the end of the first year. The corporation is certainly better off. There's a net comparison of the two over 3 years. There's a summary. In the fourth generation, the real savings have come, first of all, from development time, but primarily they come, the real benefits to the corporation, that you got so many more projects that you're getting savings from. We completed 22 projects with the fourth generation, 4 projects with the third. The break-even quarter was 3 versus 11. The net benefits, $938,000 versus $23,000. A second benefit is that people can deal directly with the computers without resorting to an intermediary. Remember our sheriff. Typically, fourth-generation languages are serving as the cornerstone of information centers being established by many corporations today. Before discussing the latest generation of languages, I'd like to say a few words about physical communications, how they're developing with the computer. That's a very important aspect of user-friendliness also. There are 2 main aspects to such communications. First is what you say. That's what we've been talking about. And secondly, there, how you say it. One way, we can look at menus. A menu is basically a user selection from a predefined choice. Prompt can be text or picture. Menus can be pre-programmed. They can be words or pictures. They're very useful for operational systems. They're very good for system use. Now, how do you make a selection from a menu? You can hit a key. This happens to be like a telephone keyboard, but a terminal keyboard, anything, you can hit a key. You can use a mouse. very high productive way of moving around. You know, you move that little thing around and then you eventually press the button. Very effective way. You can touch the screen. One defect of that is that the screen gets pretty dirty at the end of the day and you have to have a bottle of Windex in order to be able to see the next day. Or, I think what's going to happen very quickly, you can use voice. I don't know whether you can see it, but there are little sound waves going from that person down to the computer. Currently, such systems have a limited vocabulary. Currently, such systems, the computer must be trained. I think this problem will be solved, and I think that this will be a way that people will eventually like best. I mean, if such systems, I'm sure all of you know of some such systems by which computer voice activated by a menu are really being developed, very often in a production line. If you go to Chicago Airport now and you want to check in, you send your bag down the little chute. Now, instead of somebody looking at the little tag and moving it around from conveyor belt to conveyor belt, they just have one person who sits there, looks at the tag, and that's basically a menu. And if it's supposed to go to Los Angeles, it says Los Angeles or LXA or whatever the abbreviation for Los Angeles is, and a computer redirects the bag to the appropriate plane. Apparently, this has really increased the effectiveness of on-time delivery of bags at O'Hare Airport. And we can, of course, use a variety of predefined languages in communicating with the computer. This happens to be music. There are a lot of very good languages for special uses. Now we're beginning to move into what the fifth generation of language, or knowledge-based systems. These fifth-generation languages are characterized by artificial intelligence, or having all the information contained in a knowledge base. The idea is to include in the software the ability to make largely correct inferences using the base of knowledge that is available to the system's software. And that's very important. The knowledge is not in the software. It's in the base of knowledge that's available to the system software. This technology is now having a profound impact on the language perspective. We are now able to teach the computer to talk to people in their own language, instead of trying to teach people to talk to the computer in a foreign language. We can look at some examples. I hope you can see that slide. That happens to be a photograph of a 3279 terminal, 35 millimeter slide of some actual terminal output. I believe that slide says that at least 4 customers ordered pumps in March. I think the answer says no. 3 did. That's a typical yes-no question. There's nothing profound about the way that sentence is structured. It could be any other way that you might ask that question. Pump happened to find out that it just is in the database. It looks at the database to find out where it is. It knows about March being a month and all of those sort of things. Another example. I think that says how many invoices were there in months 3, 4, 5 in 1975 or 1976. This happens to be a small database of some sales data that dates back to 75 and 76. In this particular case, the answer is 19, a typical how many question. That could have just as easily said March, April, May. Could have any other question, any other way of stating that. Presumably, the comprehension program would get what you mean, look up in the knowledge base and find out where the thing is. Here's another question. What were our total profits for each product? In this particular case, you see several things. First of all, I can tell you, it's not obvious from that question, the database does not have any information in it about profit. It has information in it about other things, and it figures out that it knows some costs and revenues, and it knows that it can calculate profit from those things, and in fact does calculate profit and display it. We're not particularly specific what we mean by product here. It knows that it has a couple of pieces of information about product, so it gives you both the information it has so that it's likely to give you what you want. Here's another kind of statement. This is not a question. This looks more like a command. I need to know the total, average, max, and min units purchased by each customer. It doesn't have to have average abbreviated. That could say average. It could say average units. It could say whatever you would like. And the report is there. Another kind of thing that goes on in these kind of English comprehension systems is here's a complex request. I think it says, first show me the total units sold to each client. Next, please, if you would, display the average units purchased. Third, what were the max units? And finally, give me the maximum units sold to each of them. In this particular case, very much like you may do to me, you say, did you mean by that? And it paraphrases it back in its kind of language. You can answer either yes or no. In this particular case, we said, yes, that's what we mean. Very important question, this question of clarification. There's the report. There's a real challenge in understanding these kind of languages. You really have to understand English. The computer needs to know both about the knowledge of the language, the rules of grammar, all of those sort of things, and knowledge about the world. That's why such systems are called knowledge-based. This slide shows one of the kind of problems that the designer of such a system, such a technology encounters. This says, Sue went to the drugstore. She found the aspirin on the shelf. She paid for it and went home. What's it? It's clear. It's the shelf. No question about that. But it's also clear to every one of us in this room, if we're literate, and we know the rules of English, so therefore we know it's the shelf, but yet by our world knowledge base, we know it's not the shelf that it's referring to. We know it's the aspirin, so therefore we make the correct inference. So a computer program, to have the same degree of literacy, must handle those kind of problems. And there's just hundreds of problems like that that have to be built into these kind of systems. The knowledge base for English understanding that I believe should be supplied with such a system is first of all a general dictionary. That's a dictionary that is very much like a Webster's dictionary or an Oxford dictionary, or I'm told here in Australia a Macquarie dictionary. It's got words in it. Knows what those words mean. It knows about parts of speech. It knows about homonyms. It knows about all of those sort of things. You might have an application-specific dictionary, one that you've defined specifically for a particular application. For example, one instance that I think is quite clear is that if I was working for Nabisco, people who make cookies, crackers, and I look up in my general dictionary, I absolutely discover that an oven is a device, a physical thing. It probably gets hot and all of those sort of things, and it cooks things. But if I'm in Nabisco and I say, how many ovens do I have, or how many ovens did I have, they don't want to know how many physical entities they have that bake cookies. An oven at Nabisco is a unit of production. It's a well-defined unit of production, so they want to know how many units of production. So oven would be something that would go into your application or file-specific dictionary. You have your database dictionary, the dictionary that defines what data is in your field of reference that you can inquire about data from, the database dictionary, an active dictionary that controls access to it, the one that goes to the structure-independent database management system. And fourthly, you need a dynamic dictionary, because if the language doesn't understand a word, the comprehension system doesn't understand a word, like I might not understand what you mean by something, and I ask you, I file it away and remember it so I can understand that word in the future. A program has to do the same thing. So those are the way the intelligence is contained in such a system as we just looked at now. I think the state of the art of such systems today is, first of all, there are commercially viable products. There are products that have moved out of the research lab, have moved out of the area of academia or wherever they might be, and have become commercially viable products. There are two such products, to my knowledge. These products offer very respectable fluency, quite a high level of fluency, and they certainly provide direct access to existing data. Now, this work that we've been talking about here, these knowledge-based systems, are very closely related to Japan's well-publicized fifth-generation computing project, where they're designing a computer that will handle many of these same functions. They're doing two things. One, they're trying to increase the speed. You really do need computing power to do some of these things. And number two, they're trying to build directly into silicon some of the things that we typically have in software today. It's clearly, based on our experience in Princeton, it's clearly possible for the Japanese to do what they're talking about doing in the time frame that they're talking about doing it, the ability for us to understand inference-based, to manipulate knowledge-based, to understand that it's within the realm of the time frame that they're talking about. It's the area that all significant systems research is now undergoing in the United States, and people are rushing headlong, probably in the rest of the world too. I don't mean to limit it just to the United States. My knowledge of what's going on in the United States is deeper. It's clear that we're moving in that direction, and we can do these things. So we can expect it. It's going to change the whole definition of fluency, computer fluency. Today, people still think that computer fluency may well be to be able to program, to understand how to manage the program counter, the things that we talked about previously. I believe it's shifting. Computer literacy now means how do I use the computer to do whatever my job is, better, very much like being a driver. Today, I think it used to be when you had a chauffeur. The chauffeur also was a master mechanic to be able to go out and tinker. Today, the definition of computer literacy will be much like a driver. There are probably many fine drivers out on the streets there who cannot repair their car. I think the direction we're heading in for using computers is consumer computing. I think there are several reasons for this. First is demand. It's now estimated today that we have that the unimplemented schedule of demand for things, there are now 42 months of backlog, average backlog in the world that's now scheduled, money authorized, staff assigned, ready to do the job, 42 months. And what's terrible about that is we're all very productive, I believe, the computer specialists of the world. We're working very hard and diligently in trying to solve these problems. We've gotten much more productive. We're using many more advanced tools. But what's terrible is that the backlog of these unimplemented applications is going to increase by 3 months in the next 12 months. So instead of having 42 months, we'll have more than 45 months. Currently, the total of fulfilled demand is about equal to the total of the scheduled demand, and the total not scheduled demand, the hidden backlog, the things that people haven't come forward and said, I'd like to do, is about equal to the total of the filled and the unscheduled demand. That's the reason for the productivity requirements of these fourth and fifth generation languages. Currently in the United States, we have about 50 million office workers, represented by these people here, all of whom, or at least some of whom, want to become more productive by having access to a computer. The figures in Australia are that you have about 4 million office workers here, according to my data. In the United States, we have about 625,000 computer specialists. Here in Australia, we're about 40,000, I'm told. Each of these people is working hard to reduce the backlog, but it keeps increasing. It seems to the average computer specialist, the better job they do, the greater the dissatisfaction on the part of the user with the growing backlog. That's really not true. But if you do some arithmetic, you discover that in the United States you have about 1 computer specialist for 80 people, and in Australia about 1 in 100. So that means in the United States each one is trying to carry about 80 people on their back, trying to make each one of them more productive and increasing the demand. Here in Australia you have to work harder. You have 100. And what happens is that you make an office worker happier. You give that manager an increased visibility, more productivity. The person has an easier job, or starts dominating meetings with more information, or whatever the reason, whatever happens. And the colleagues pretty soon see that this person has become more productive. It's a competitive society. We just saw a boat race. Clearly a competitive society. But the same thing happens in the office. I become more productive, or you become more productive. I say I want something, so I run down to my computer specialist and say, do this for me. The demand escalates, and the world continues. So really, while all this dissatisfaction is going on, it's really caused by complete and absolute satisfaction. But the problem's not going to be solved by producing more computer specialists, because the growth is slow. Currently, we're increasing computer specialists at the rate of about 4% per year. And I don't think it would be possible to create a ratio that would do that. I mean, what it would mean is we'd have to do is convert all the computer specialists into office workers so that they would do all the work of the office. Therefore, what we're talking about is basically transferring the work to the office workers, just as the phone company did. I think that an analogy is very good. Phone service used to be very personalized. We had specialists who were called operators. You could make telephone calls. Just called up an operator and asked them to do something for you. Telephone company did some arithmetic back in the late 30s, discovered that if calls continued to increase at the rate that they were increasing, that they're pretty soon that they would need in order to handle the rate of calls that they would forecast, which in fact has materialized, they would need more operators than there are people in the world to handle that volume of calls. Any smart business person can recognize that that's an infeasible situation. So they started to mechanize. They basically transferred the work in a fairly user-friendly way to the people. Everybody makes their own calls. You now you can dial in your own credit card number. You make your international calls. Everything happens. It's basically, and the same thing has to happen here in the computer world. So in summary, one reason for the consumer computing is because the demand exceeds the supply. The second reason is because that information consumers may, in some cases, be more effective. When an information consumer works directly with a computer specialist, there are lots of communications problems. We've been discussing those earlier. These can cause delays, misunderstandings, and in many cases, and in most cases, are wasting the valuable time of a very scarce resource, the computer specialist. In those cases where the information consumer can work directly with the computer, these communication problems are done away with. The trick is to give the information consumer the tools that he or she needs so they can deal directly without the need for an intermediary. This force has clearly been the driving force behind the technology that has moving us to the that has moved us to the fourth generation and is now pushing us to the fifth generation. This is data from a study that was made by CZ, a research institute at MIT. Basically, it says that in 1981, about 5% of total computing resources was used by consumer computing. They showed that they predicted that by 1991, 75% would be used by consumer computing. This doesn't say that the amount of computing that's been used by applications that have been developed by computer specialists for others to use, the 25% in 1991, will be a smaller amount. It'll be vastly greater. It just means that the ratio has changed. One question some computer specialists ask is does this mean that computer specialists are becoming redundant? The answer to that is clearly no. First, computer specialists will always be the people who are developing the routine operational systems, be it directly in-house or working for a software vendor who's developing application products or systems products for resale. This software will always become more complex and ever far-reaching. The cost ratio between hardware and people is changing. It's just driving that. For example, in 1981, we saw that it became economically feasible, economically desirable, to substitute 1 hour of computer time for an hour of person time. It was an economic trade-off. So all the systems that had been designed with earlier economics had to be redone. So you wanted to redo those systems. By 1986, if cost trends continue, it will be economically attractive to trade off 1 hour of computer for 6 minutes of a person's time. Thus, additional revisions to operational systems will be desired, always growing forward, driving forward. Second, I see that the information consumer will always require assistance. I think the backlog will be with us for a long time to come. Now I'd like to close by discussing a few key issues. The first I see is mainframe or micro, something that we're all interested in. In this case, I think the answer is very clear. It's neither. The answer is that we ought to combine the mainframe and the micro because we achieve a lower hardware cost. We increase our very large investments in data. This requires the same system software at both ends of the link so people can talk to each other, the software can talk to each other. Why do we need the investments in data? Let's look at what's happened over the past 20 years. 20-odd years ago, if you went to a meeting, the first thing that you did was that you went there. The meeting might be called, what should I do about my advertising budget? So everybody would start sitting down and argue about who had the right data. The meeting was over. You'd never discussed the problem, and you probably hadn't resolved on who had the right data. Then we began to put this massive investment into database management systems. It's largely resolved this problem of redundant data. We have very good databases. I actually go to meetings now where I observe people arguing about the problem and not about who has the right data. If we go and if you allow your corporation to go and have all the data go back to little microcomputers and take them off the mainframe, you will have the same thing all over again, and we can go back to not solving problems. Another question is, what should I do about software? The characteristics you need for software are, it has to be easy to use, we've talked about that. It has to be easy to use even on an infrequent basis. One of the important things now about software, very important factor when you're designing your systems, is that people will come to them and use them now, and they might be very naive, very unskilled. A few weeks later, or you are using it, you might be very skilled. But this naive person, sometimes their skill level increases with time. So the software always has to have a constantly evolving interface to keep it in tune with the current skill level. And just because my skill level gets up to here today, I may stop using the computer for weeks, months. I come back a few days, whenever I come back, my skill level retards, but now my growth rate is much faster. And to keep that software in tune with that skill level is really one of the major challenges facing all of us today who design software. It's got to be able to meet increasingly sophisticated demands. The cost, changing in the cost economics are causing the demands to go up. One of the significant uses of computing today is no longer keeping track of the books, but it's really forcing the whole marketing issues in corporations. They're using computers in aggressive marketing outreach to help the company sell its products. And they got to be reliably and efficient. I think what you really need is a complete software solution. Most software solutions today are narrowly defined for specific needs, but complete products are beginning to appear. Benefits of a complete solution are you spend less time building bridges. An awful lot of time today is spent building bridges between different packages. Decision support can be added to production applications. Very, very important. Really optimizing the use of that data that you've spent a lot of money to collect. And training costs are lower, and productivity is much higher. Another question you may be asking now is, what about fourth generation and fifth generation? If we are still in third generation, should we skip the fourth generation and wait for the fifth generation? I think the answer is no. First, fourth generation languages will continue to be the best way to build applications and application products. Second, even if it was not true, the typical payback period for a fourth generation language is very small, perhaps less than a year. So it's a wise investment at any time. Fifth generation systems are here and can be used by the information consumer. They should be adopted. The fifth generation products will not be suitable products for application development for some time to come, but will be an integral part of a complete system so that computer specialists have access to the fourth generation technology and the information consumers to the fifth generation, all in one system. Another question that concerns some people is what about proper use? There seems to be some worry, especially among some members of our top management of some of our corporations, about consumer computing and putting computer terminals, little computers all over the place. They say, how do we know that people will make appropriate use of the computer? Maybe they'll even play games. First of all, it's not possible to control. It can only be implemented with good staff selection and motivation. Second, the best strategy is to charge for all your resources, your computer resources. This puts budget and expenditure control at the people who use the computing resource, not at some central authority who makes godlike decisions. But it puts a level of expenditure control where it belongs, the people who are responsible for justifying it. And that's the only way you can control it. In the last few minutes, I have touched briefly on the 5 significant generations of computer languages and some of the impacts of the newer 2 generations of languages are having on bringing us computing power directly to the information consumer. I have not said much about the impact of these newer generation of languages are having on application building. I think the impact is obvious to you. They can both enrich your job by letting you concentrate on the more significant problems, and they make it more rewarding by increasing your productivity. I said I was going to ask why we aren't taking full advantage of all the new language technology we have today. Why is COBOL still so prevalent? I can't answer that question. First of all, I have to say that I have a bias. I can see that it is possible. What is possible? I see the gigantic advantages that some people are getting individually. And I see that companies, some of the advantages there are achieving great success. For example, by taking market share away from their competitors, and in many cases by doing so by applying their information processing technology more productively. In closing, I'd like to say I hope your installation is capitalizing on this technology, and if it is not, it will be doing so soon, and you will have the privilege of playing a very important role in the continuing information revolution. I hope these comments may be helpful to you. I'm certainly willing to take any questions that you may have and have any dialogue. I really thank you for your attention. Thank you very much.
For those of your questions, and I'm sure many must, would you come forward? Where's the microphone?
Right behind the...
Right behind the projector. Would you come forward and state your affiliation and then ask your question? And who would like to be first? There's one there. Thank you.
Kevin Moisey, Pete Mowick, Mitchell Services, Adelaide. I'd be interested to hear your comments on what you see the marketplace for package software being. That is, apart from packages that support 4th generation languages per se. That is, application software.
I think the market for application products, which I was not addressing, I think is a very important market. I believe that it's very important that people are buying applications as opposed to trying to help develop them themselves. You can see that people are now buying general ledgers. There's hardly anybody who builds a homegrown payroll system. People are buying banking systems. I think what you're going to see is a real change in the development of applications. You're going to see that people are developing the application vendors especially are going to begin to develop these applications in 4th generation technologies as opposed to 3rd generation technologies for several reasons. One, they become more flexible. They can be more easily modified to special situations. And if they are modified, they are then still maintainable. And that's a very important factor to software vendors, because if they sell source code and then you might modify it, they can no longer get maintenance revenue, and they really like maintenance revenue because that's good for their business. and it gives them an advantage of tying into decision support. But I think that you'll see the markets for both, all kinds of products, software products developed outside of the using organization, continuing to grow very, very rapidly. Certainly the forecast by all the organizations who make such market forecasts show very rapid growth.
Great, thanks very much. John Patrick, Deakin University. I'd like to ask a more technical question about English language dialogue, of which you've shown us some fine examples. I wonder if you could tell us how the systems tackle the problem of exactly what information is wanted to be retrieved by the user. And if I can expand that with an example, if you had something like an employee database, you could ask a question: who lives outside Melbourne, is under 30 and have a salary of greater than $20,000. Nowhere is it clearly stated exactly what information is wanted to be retrieved. Do you want just a Christian name, just a surname? People could use fairly simple ad hoc ways of answering, deciding, but an ad hoc way isn't particularly useful for building large systems. Could you tell us what they use and what perhaps is on the cards?
There is two ways, I think, that there are two answers to that question. First of all, that this really is a production application. This is a personnel system, a system that you really have put some time and effort into in expanding the dialogue. Then the question is going to be that you will have defined some information in your file-specific dictionary. You will have expanded on what is meant in your specific question, I believe, by the word who. That becomes data, becomes part of the reference data, what people usually mean by who. On the second hand, if that has not been done, and it's an ad hoc type of situation, then our policy is when you get a word like who, is very much like I would do with you. I would ask you, what information do you want relative to who? I could give you A, B, C, D, and E, and then you would have to tell me what you would like. I think that's a very important place to have user dialogue. Now, if you had said with a dynamic thing, what I mean by who is this, from then on, that's what we would mean by who for the duration of that session, because we would believe that that's what you continue to mean, and then you would have to rechange that. Gentleman right over in here, yeah.
Gerald Siegel. I found your ideas about the fifth generation very exciting, as they appear to bring computing down to grassroots level. However, it seemed to me that the fifth generation implementations, it sounds as if it's really for mainframes, and I wondered if you had any ideas when these principles perhaps would become available to the general public on, say, personal computers.
It depends a lot on what you mean by a personal computer. Small-scale workstation computers are going to become much more powerful. We need more computing power than is typically available in an 8-bit or even some of the 16-bit micros. Certainly some of the 16-bit chips that are available today are capable of supporting this. If you mean by a personal computer a workstation that might sell in the range of hardware for $30,000, as opposed to $13,000, but let's pick a number of $30,000, then the answer would be, and it requires no environmental maintenance and it just sits on your desk, then the answer would be October 1983. If you mean $13,000 computers, you probably mean 1985. That's in the realm of the hardware manufacturers, how soon they would like to announce some of the products that they could announce, given that they felt that the market was right and would not eat up some of the demand that they have for their current generation of small computers. But there are computers available today that are of $30,000 class, of which at least the product of which I'm most familiar with for English comprehension does in fact run on.
Richard Hibbard Computer Systems. One of the criticisms that's regularly pointed at fourth generation languages is that it only really addresses itself at 20% of the total EDP installation problem, the cutting of the code. What is your comment on this, please?
What's the other 80%?
Oh, the investigation, we're going back to traditional approaches to it, is the investigation stage, the design stage, the cutting of the code and so on, and then the installation and the debugging of the production installation stage.
Well, yes, I think that fourth generation languages do have the most impact on implementation and have less impact on design. But I think that they have a very major impact on design. Nevertheless, I think one of the biggest problems in design is the communications between people and computers, between the different people, between the user and, say, the computer specialist who's designing the system. The whole advent of prototyping, the whole advent of having procedures that both sides can understand, really lead to much more rapid design. Now, in some sense, that answer begs your question, because in fact they do have, there still is probably more that can be done. I think some major advances are being made in that area with other kind of technology to support that process, feeding into fourth generation languages. For example, just last week I was looking at some technology that seems to be coming available, that if I would write a flowchart out, sort of the procedure, not a flowchart of the program, but a flowchart of what I would like to accomplish, it looks like I can take that flowchart that is expressed in English and translate that directly into a fourth generation language, which does speed up the specification process. Now, that's not a promise, what I just said. It just says that it looks like that technology is beginning to be available.
Thank you.
Thanks. There's somebody over there in the back.
Roger Clark, Summix Consultancy. Dick, I'm a skeptic about knowledge-based systems, and I was horrified by one of your slides. Let me cast back a little to a situation where we're supplying printouts or displays of information to users. We supply them to them over periods of months and years, and they always look the same, and the interpretations that the users must make of the data on those sheets of paper or on those screens remains much the same. And users can still hopelessly misunderstand what the real intended information content was. Now, you're going to shift the ground underneath their feet. You're going to assume that the knowledge that you've been able to insert into the machine is going to be in the head and in the conscious part of the head of the user. And if I can refer back to that slide that you used, which showed a question like, what's the profit on these products, please? I wonder what interpretation the user would place on that. Was it month to date, year to date, last month, last year? There are many different bases for calculating profit. The machine might know. If the machine doesn't confirm back the list of 37 assumptions it's made, most of which will be reasonable and one or two of which might not be, how is the user going to come out with the right understanding? It's back to the Tower of Babel problem that you yourself referred to.
The what problem?
The Tower of Babel.
Yes.
What do we really mean by these signs?
Yes. There are several things that you can do. One of the ways that you can, in fact, use the system that the procedure that I just showed, is that, in fact, you can take and ask it to, every time it answers a question, to give you back basically a listing of all of the assumptions it's used. How is it calculated profit? What is the reference base? All of those sort of things. You still can't ask it to take and tell you what the data is that is in the file that you're referencing, which file it is. There still are a lot of assumptions, yes. We're equating quite a bit of, I think in any knowledge-based system, you are giving quite a bit of intelligence credit for intelligence to the people who are using the system. I think we're also giving quite a bit of, in my personal bias is, that we're also giving a great deal of intelligence to the average executive who's running our businesses today. And if they're confused about the assumptions, at least in the meetings that I have gone to or in the places I've gone to, they've never been shy about asking. I think what it does do by putting a person in dialogue with a computer is that it doesn't so much disguise the role of what's going on. I think one of the biggest problems we have, and I suffer from that, and I think all of us suffer from that, if it's on a computer printout, it must be right because the computer said so, but we all know that that's wrong. I think that having it come up on a screen, having it come up in an interactive way, or having it respond back by voice or what have you, sort of makes it a little bit more personal. And I would hope in the long range is going to cause the person who's interacting with the database to challenge what's coming out a little bit more aggressively, just as they do what happens in interactive personal meetings. And I think that's one of the advantages of personal meetings. So yes, you're not going to take and do away with those kind of problems because we have those kind of communications problems. I think it helps it, though.
Good. Thanks, Dick.
I think we'll have time for one more. Thank you very much. I think we've heard a rather important speech here. I could only think of one thing while I was sitting here that was probably that most computer programmers are unaware of. I teach computer programming to highly motivated, intelligent, well-educated adults. 20% of them have a mental block against the operation of a von Neumann pointer. In my course, I call it basic line numbers. They cannot see the jumps in their mind. 80% of my students, and this would include many of your bosses, are willing to go along with the concept but feel uncomfortable with it. And a business which depends upon the von Neumann pointer, a new phrase in my vocabulary now that I've heard Mr. Cobb's speech, is something which is a shaky business indeed, because as the computer becomes more and more important, business just isn't going to be able to live with the restrictions that they have now. And I think we've heard a very important speech here. You may feel safe with COBOL, but when the crash comes, it will just be bigger the longer it's held off. And with that, I want to thank you for a very important speech, and we have a little memento. I'll have to give a speech at the next conference 2 years from now so I can get one of these. We'd like to thank you for your help, because a conference is a lot of pretty displays, but it's not really a conference unless you have a chance to meet people and see where the world is going. And so I'd like to present you with that as being an important part of our conference.
Well, thank you very, very much.
And because I was just thinking all the people who have to travel with that on airplanes, I hope they get home all right. And the other thing is that I hope that you have had time. I understand this is your first trip to Australia.
That's true.
And I'm sorry that you haven't had a time to take a look around Victoria, but that's a book, Discover Victoria, which will give you an idea of some of the beauties that you've missed, and you'll have to come down and make a longer visit.
Oh. People are too kind to...
In 1964, the American Air Force decided on a one-week decision that they would no longer buy analog plate simulators, but only buy digital. My company had 400 years of analog plate simulators, and a year later, 200 of them were lost. Because they couldn't make the translation.
I guess one of them is coming in essentially.
That happened. The sand was shifting, and everybody was living in a fool's paradise. And then all of a sudden, there was a huge crunch.
There is...
No, sorry, you should have moved me out.
A program that is, quote, intellect,
Was I in the way?
was marketed by a company called Artificial
Just sort of wandering in as well.
Intelligence.